So folks, I've had a few questions about this question here. This is number 6 in the section 1.2 My Math Lab, or if you like, from the textbook, this is question number 29 from section 1.2. So I'll let you read through this problem on your own. But in this case, we are given the object's acceleration. But it's as opposed to maybe how you might see this problem posed in Calculus 1, rather than writing a of t, they've written dv dt, so it looks like a differential equation. It's not a very exciting differential equation, and we're not going to need any unusual techniques to solve it, but it is a differential equation nonetheless. We've got the derivative of v showing up as well as the independent variable time. So all we need to do to solve this is to integrate both sides. So if we integrate both sides, we'd have, the integral of dv dt is equal to the integral of 0.15 t squared plus 0.3 t dt. And so by the fundamental theorem of calculus, we end up with just v of t on the left-hand side there. And on the right-hand side, we'd have, I'm going to write that as, well, this would be 0.15 divided by 3, which is 0.05. But I'll go ahead and write that as 5/100ths t cubed plus, and then we have, let's see, that's the same thing as 3/10. And if I divide that by 2, we'd have 3/20ths t squared, and then we have a constant. Okay. So we're told that the initial velocity is 0, that is, v sub 0 needs to equal 0, and I'll let you check that, but the only way that could happen is if your constant's 0. And so we end up with v of t, our velocity function here, is 100 t cubed plus 3/20 t squared plus c. Folks, I encourage you not to become complacent. A lot of times our initial condition is when time is 0, it outputs a 0, and that oftentimes makes a polynomial. If it's a polynomial, the constant will come out to be 0. Just be careful with that, because that won't always be the case, and sometimes you'll actually have to be solving for those constants, so don't get complacent there. But in this case, we would have that this constant is just 0, and there's no need to write it out. So we've now got our velocity function here. Folks, be careful. This question sort of comes about in the wrong, an order you wouldn't quite expect. It asks for how far the car travels in the first 10 seconds. It doesn't ask what the car's velocity is in the first 10 seconds. So we are not ready to answer this first question with the problem. So the next thing we need to do is we need to find the displacement function. So if typically we use s to represent displacement. So what we need to remember here is that s of t is, well, in fact, we could say that ds dt is our velocity. So ds dt is our velocity function. So this is just something that we got to recall from Calc 1, that this is the derivative of displacement. And we remember from Calc 1 that that is velocity. So what we need to do here is we need to go ahead and integrate both sides. So if we integrate ds dt, that's equal to the integral of 5/100ths t cubed plus 3/20ths t squared dt. And integrating, what we end up with is, let's see here, this would be 5/400 t to the 4th plus 3/60 t cubed plus c, and that gives us our s of t. So there we have the general form of our displacement function, and then again we use that initial condition that says that the displacement when time is 0 needs to be 0. By the way, it looks like they're using the letter x for displacement. I used s, so you could change this to, if you wanted to, x of t, but for me to be consistent, I'm going to keep it at s of t since that's how I started doing it. Okay, so using that initial bit of information, we said that s of 0 needs to equal 0. So again, and don't get complacent in this, but in this case it means that the constant is 0. So I think we're ready to give now the position function. Our position function is s of t equals, and let's do some reducing here. That reduces down to 1/80 t to the 4th. This reduces down to 1/20 t cubed, and then that understood constant's 0, and there's no need to write it. So here we've got our velocity function, and we've got our position function, which we obtained by solving these very straightforward differential equations. When I say straightforward, I just mean that there is no difference between the techniques we used in this class right now and what you would have used in an earlier calculus class. So now we need to decide how to answer the two questions, and I've only pulled up one of those here. This is a question about how far the car travels in 10 seconds. So to compute that, you'll compute s of 10. We get 1 over 80 times 10 to the 4th plus 1 over 20 times 10 to the 3rd. And if you crunch that, let me do that on a calculator. So when I do that on a calculator, I get 175, and it's implied then that this is 175 what? Well, our acceleration was measured in feet per second squared, so our position or displacement is measured in 175 feet. The second question asks how fast is the car traveling? In fact, I think it's probably more precise. It probably says, what is the car's velocity? What is the velocity after 10 seconds? And so for that, you would compute v of 10, and so you would plug that 10 seconds into our velocity function. And I believe when you do this, you end up with 65, which gives us 65 what? Well, our units would be feet per second, given that this is velocity. I hope this helps, folks. I'll be making another video for some more of these problems.